Hello and welcome to today's webinar, Leveraging Aluminum's Attributes for Effective Extruded Solutions, brought to you by Design World Magazine and SAPA Extrusion North America. I'm your moderator, Lisa Eitel, engineer editor with Design World Magazine. Before we begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply ask for help through the Q&A box on your On24 console. That's on the left-hand side there on your screen by default, but please feel free to move the windows around. Also, get social and share information from today's session. Tweet or post on this webinar and hashtag your post to join the conversation with hashtag DWWebinar. Direct contact information for me and your presenter is accessible through that contact window. We also welcome your questions relating to the presentation. Just answer your questions as they occur to you in the Q&A window. We will answer as many questions as possible during an interactive session that will follow the main presentation, but please feel free to type in your queries at any time. Now we thank our presenter, Jason Weber, for being here. With more than 20 years of experience in the aluminum extrusion industry, Weber and his team are responsible for increasing extruded aluminum content and developing local and global product strategies within the energy and industrial product segments. Weber is a member of the Aluminum Extruders Council with a seat on the AEC's Board of Directors. He is also leader of the AEC Solar Electrical Emerging Markets and Defend Seed team, aimed at identifying end uses with growth potential for aluminum extrusions and developing industry platforms to boost extrusion use. Now let me hand the mic to Jason. The floor is yours.
Thank you, Lisa, for that kind introduction. Good day, everyone. I'm happy to present to you today the Leveraging Aluminum Attributes for Effective Extruded Solutions. Today's webinar is brought to you by the AEC. The Aluminum Extruders Council, or the AEC, is the industry association for the North American aluminum extruders, with approximately 60 extruder members accounting for 75% of the extrusions produced in North America today. The AEC is focused on user education in presenting webinars as we are today. Also, there's a track for member excellence for the extruders, as well as fair trade. For SAPA, SAPA is the world's largest aluminum extrusion company. SAPA is an AEC member operating 22 North American production locations. In addition to our North American locations, we also operate additional 80 locations globally in Europe and Asia. The agenda for today will follow two basic tracks. We'll talk about the extrusion process, the attributes of aluminum extrusions and how to leverage them, with three key takeaways. We'll talk about the alloy selection, the extrusion geometry, and then also delve a little bit into fabrication and finishing. Obviously, with the extrusions, we're talking about the shapes, and the shape is the idea that you, the designers or the engineers, come up with. Obviously, almost any shape can be produced as long as it'll fit within the circle size of a particular press, which happens to be the limiting factor of the aluminum extrusion process. As an introduction, we'll talk about the right geometry. We'll also talk about the alloys and the designer's use of fabrication and finishing to create effective product solution. And on this particular slide, we have highlighted four examples of different uses of the design and alloy characteristics and fabrication operations within aluminum extrusions. In the upper left-hand corner, you actually see an LED light where that outside diffuser cover is actually a fabricated anodized aluminum extrusion. In the bottom left, we have the nodes, which are creating the structure of that particular part there, as well as heat sink applications when we're looking at MRIs or CAT scan machines, and also LED light bars. In addition to the functional and decorative applications we see today, we're using aluminum extrusions in high-intensity LED applications, such as the medical light that you see in the upper left-hand corner, as well as intense structural applications as with the Ford F-150 in the upper right corner. And then the decorative applications is in the bottom right with the fencing structure. We'll talk about that one later throughout the presentation, as well as the decorative finishes in consumer electronics, where you look at the new Apple Watch with the extruded aluminum and anodized case. Overall, the extrusion process is fairly simple. We're talking about forcing a material through an opening in a piece of tool steel. A very simple example of this is the Play-Doh press. Here you can see the Play-Doh press, which maybe either our children or we as children played with as a youngster, where you actually have the shapes cut into that plastic piece that sits at basically the mouth of the press. The Play-Doh or the material is put in the back, and then it's forced through that hole. So the material itself has no choice but to come through that hole and to take the shape of the opening that was cut. An interesting thing about the aluminum extrusion process is what most people want to know is how do we create hollow profiles. Hollow profiles are relatively simple in that when the billet is forced through the die itself, the die is fixed with a mandrel in the middle, and then you would have the bracing for the mandrel on either side of the larger opening. The billet itself, once it's forced through that opening, is actually broke into two separate or sometimes multiple pieces. And then as it flows back through the larger opening, is basically welded back together and forms the tube as you would see it in the lower right-hand corner of the screen. So again, the extrusion process, as we know it today as an aluminum extruder, is much the same. We have a preheated aluminum alloy billet that we force through high pressure through a piece of tool steel. And then as that material flows through the tool steel, it takes on the shapes in the pockets, and then it emerges from the press in the desired shape that was created as it flowed through the die itself. Here's an overview, a very basic overview of the extrusion process. As I said before, we start with the heating furnace, where we'll preheat the billets, or in some cases logs. Those are then placed into the extrusion press, which is where the die is fixed onto the front of that press. So in this particular illustration on the far right-hand side of the extrusion press, once that billet is forced through the press, the die, it'll emerge onto a runout table and can most times be a couple hundred feet in length. There would be a rough cut sawing operation onto that on that particular part there, and then the extrusion, the long length extrusion, would be presented to the stretcher, and the stretcher will pull it, clamp onto both the front and the end of the profile and stretch it straight. A finishing saw operation will cut it to a shorter length than what was extruded, and then the extrusions will be placed into the aging oven, where they will receive their final temper. As part of the extrusion process, we also put into the parts themselves is where they receive their temper in the final age oven practice, as well as how we treat them as we are extruding the profiles. Here you can see some of the typical tempers that are referenced within extrusion. The most common being the T1 through T6. Those would typically be the most common tempers that you would see associated with the different alloys that are produced. There are some other alloys, as in the O temper, which would be for fully annealed material, which could be things like impact rod and or parts that need to receive a severe bend. F temper material, which would be things such as forging stock, and then the strain hardening tempers like an H112, which actually receives some hard working after extrusion. The extrusion process really marries up or takes advantage of the attributes of aluminum with the extrusion process. Seen here is a very long list of the different attributes of extrusion as well as aluminum. We will primarily just discuss a few of these as we don't have enough time to really go through and talk of all of them in detail. However, some of the most important as we talk about aluminum is the high strength to weight ratio, its conductivity properties, as well as its suitability for the integral shapes and production to close tolerances. Also talk about the decorative attributes of aluminum and extrusions as we can, apply many different finishes to the parts. And then the ease of fabrication. So as we go through the next part of the presentation, we'll talk about several different products or projects that have utilized aluminum extrusions to create an efficient part. With the high strength to weight ratio being a key attribute to aluminum, we can see here that in some alloys of aluminum, this one in particular is 6082 alloy, which is a structural alloy in comparison with mild steel. You can see that the ultimate tensile strength is much the same. However, the density of steel is much greater than aluminum. So when you look at it on a strength to weight ratio, you can sometimes yield a part that is almost nearly as strong as a comparable steel part, yet is a third as dense as steel, and therefore will typically weigh sometimes as much as half as the weight of the steel part. So one of the industries right now that's really taking hold and working on a lot of conversions of not only steel to aluminum, but different forms into extrusion, so casting to extrusions, forged parts into extrusion, is the automotive industry. So obviously in the automotive industry, weight is key in creating efficient vehicles, in reducing the weight, but also stronger and safer vehicles. Here we can see just a couple applications in use today. The first picture to let's say the upper left is a Ford F-150 roof bow. Another roof bow for the Tesla Model S is below that. And then you have the C7 Corvette frame, which is an aluminum structure, is 90 pounds lighter, but 60% stiffer than the prior steel construction. So as we start to talk about more efficient vehicles, we need to be able to create stiffer and, most importantly, safer structures for use in the automotive industry. But a key in this is not only the material, the aluminum material, but then also the profile design. As you can see in a lot of these profiles, specifically in the Tesla Model S roof bow, which is the profile on the bottom, the wall thickness of the part is not uniform around the entire profile. And with an aluminum extrusion, you can actually move the metal and only put material where the material is needed. So therefore, you're not only creating a stronger structure in being able to customize where that material goes, but also a more cost-effective structure because you're not putting more material in there than what is needed. Here's an example in basically a bridge application. So here in building and construction, which is actually where weight not only is important because you need to be able to transport this, but also because you are assembling this in the field. So with this particular application, you're looking at transporting this into remote locations by a truck or a helicopter, which is very important to have a lightweight structure. But then you're also looking at quick assembly, is assembling a bridge in only an hour and a half with a relatively few number of workers, in this case 10 to 12. But yet it can span up to 60 feet. And it uses really nothing out of the ordinary as far as alloy and tempers, right? 6061 T6, 6005 AT6 are both very standard and very commonly used in extrusions today. There's no welding needed, and it's only assembled by the use of bolts and pins. So here is an example of where design is coming together in conjunction with the attributes of aluminum to make an efficient relocatable structure. Another interesting point about aluminum is the fact that as it gets colder, there is no adverse impacts on the material itself. Obviously, that's important today for this gentleman right here who's on his snowmobile doing some kind of flip, where you actually have that aluminum structure that is operating in a cold environment that, when they land, it's actually not going to crumple. Probably a better real-life scenario in talking about is the fact that when a plane is operating at altitude, it's negative 70, 80 degrees Fahrenheit, and that's a place where we do not want brittle material operating. So aluminum is very key in the fact that it not only gains strength as it gets colder, but it actually becomes more ductile as well. So going further on the conductivity, specifically of temperature, aluminum is a very efficient conductor of temperature as well as electricity. But here we'll just talk about the temperature aspects of the conductivity of aluminum. Here we go with basically three separate graphs. From left to right, we talk about the thermal conductivity properties of aluminum. So you can see how that relates to brass, copper, magnesium, nickel, and silver, with copper and silver being better than aluminum in thermal conductivity. The next graph is density, where you actually see where silver is actually less dense, more is some of the highest density, but the only one that's really less dense is magnesium than that. But then when you put basically the two together, you do more of a value calculation. The biggest bang for the buck actually comes in when you're using aluminum, because it has one of the lowest densities, plus is one of the better thermal conductors. And then bringing those features together, you actually have a very efficient thermal conductor, which is why you'll see aluminum used, extrusions used from LED lighting to heat sinks to cold plates to electrical enclosures, plus also other types of electrical bus conductors. So here again, with the relatively ease of design and production of an aluminum extrusion, that's why you'll see it in all those various different types of thermal products that I just mentioned. But one other important attribute of extrusion itself is it's a forging operation. So when you compare forging operations to something like casting, you'll actually see much less porosity in a forge than you would in a casting. So in a heat sink application or a conductor application, porosity is a very important item in controlling the efficiency of that particular unit. So typically, just in switching from a casting to an extrusion, you will gain something like 5 to 8% efficiency just in switching types of production methods. So here we see another opportunity in LED lighting, where we're looking at having to conduct large amounts of heat, because in this particular one is an LED light bar for an off-road vehicle application. You can see it on top on the vehicle there. So it's throwing out huge amounts of light, which is generating an enormous amount of heat, which needs to be removed through the heat sink on the back of the LED profile. However, in this particular vehicle application, the need is also there to mimic the surface of the vehicle and actually bend it. So with the aluminum extrusion, this one is actually stretch formed in a T4 condition and then heat treated to a T6 condition, so it can mimic the front end of that vehicle that it's been installed on. So again, using the formability and the ductility of aluminum along with the thermal properties of aluminum. And in this one, it's also anodized black, so there you're using the finishing attributes of aluminum to be able to create a part for an off-road automotive application. Here's another one in the automotive space or the transportation space. This in particular is a motor housing for a truck or a bus. So here you would have one of these motors on each of the drive wheels of the vehicle. It's important to note, so here obviously we're using the thermal attributes of aluminum itself, but then we're also using the extrusion benefits in being able to create hollow profiles. This picture is not detailed enough, but inside each one of those profiles you would also see serrations, which increase the surface area within those hollow profiles, which helps make the basically the heat sink properties of this profile better, in that there is fluid that is being passed through those channels in cooling this electrical motor that you see there. So we have again with the heat conductive properties, here's one where we've actually utilized the extrusion properties and let's say tips and tricks within extrusion and how you join extrusions or affix extrusions onto other parts. In this particular heat sink, where the heat sink on the right is mounted onto the back of the LED light source on the left, and actually they've placed screw bosses at the required positions within the extrusion itself to be able to mount directly onto the LED light board with no additional machining required. And again, as with the motor housing before, if you could see the individual fins here, you would actually see the serrations that were put onto the fins to increase the surface area, making it a more effective conductor of heat. Again, coming back with the heat conductive, this is an interesting case in that you have one extrusion on either side. You can see in the bottom left-hand corner of that picture there. So it's the same extrusion put on either side of the assembly. This is an illuminator viewing hood housing for a steam water gauge in an industrial application. So in this one, with taking advantage of the design characteristics and the ability to extrude complex profiles, they've actually taken and added in all the particular bolt slots, screw bosses into the extrusion itself, and have basically eliminated 30 to 100 welds depending on the size of the unit in question. So it goes together through a slide assembly. And then with this one, they also added the cooling fins onto the extrusion itself. So the only thing really you have to pay for there is just the additional material that goes into the cooling fins. So those are just added just as a natural part of the extrusion process. The next several slides will begin to talk more about these integral shapes. This is just a picture of what we call the idea profile. It's not really a real world profile that's used anywhere, but it does give you the idea of all the different types of mating features that could be put into extrusion, from a hinge detail to screw bosses to bolt or rivet slots, to then the decorative fluted appearance that you would see on the bottom left-hand corner of that extrusion, to snap fit and just the heat sink. So it gives you kind of all in one shape a lot of the different features that you can build right into aluminum profiles. So as we start talking about the aluminum profiles a little bit more, we start talking about the integral shapes. And a little bit later in the presentation, we'll start to talk about the economics of a shape and the cost associated with the development of the different dies and everything that goes together. So like with the automotive applications before, this is an instrument panel beam. So one of the interesting things about this is that these particular beams, obviously there's one in every car, but they're very part intense, right? This particular one for extrusion uses 19 separate extrusions to make up all these different support structures as well as the brackets that go onto it. But the interesting thing about this, and what we'll talk a little bit more about later in the presentation, is to do this in extrusion with the extrusion tooling required is much more cost effective than it would be to develop individual stamping dies, casting dies, maybe some forging dies, depending on the requirements of the parts, we can easily do it very quickly and very economically with extruded aluminum profiles. Here's another one in a healthcare application where basically you have telescopic profiles. So here you have basically 3 to 4 different profiles that will come together that will create this structure on the left-hand side of the screen, which goes across and basically enables the movement of people out of beds or in and out of chairs if they're unable to do it themselves. But basically, just a few profiles integrated together can create a very modular structure that's able to be customized depending on the setting that it's installed into. This is probably one of my favorite examples out of the automotive industry. In this particular one, we've all seen some of the newer vehicles out there now with the panoramic sunroof in it. In this particular one, we have basically 2 extrusions, 1 extrusion profile, 2 extrusions that have come together to eliminate 28 parts that made up that steel mechanism. So you have the 2 extrusions, which are red on either side, and then you have 4 stamped parts for the connectors in the middle, or cross members in the middle, as well as the end caps. But a very interesting example where you can integrate into one profile all the different features that are needed to create this movable glass structure that basically sits on top of a vehicle. It's very interesting. All the ports for the sliding mechanism for the glass, the mounting features for mounting it to the vehicle, all that is integrated into these profiles. Here's another one from the automotive world where we start talking about integrated profiles and multi-hollow profiles, where we've incorporated these internal stiffeners, the webs on the inside of the hollow profile, to create the necessary strength within the profile that this can be used for, as in this particular application, is a floor on a Mercedes vehicle. Another interesting part on this particular application is that this part incorporates friction stir welding as the method of assembling basically 3 multi-hollow profiles together. So friction stir welding is a solid state welding method where no filler material is put into the joints. It's basically done with a high-speed rotating bit or tool that is pulled through the material and heats the material and basically fuses it together as the tool passes. So very interesting use of multiple types of processes to create that one profile. As we discussed a little bit earlier, range of finishes is very important because obviously not only do we see a range of finishes that are used for decorative applications, but also to reduce corrosion or provide some other type of feature to the profile as well. So aluminum accepts a wide variety of finishes from paint, either wet or powder, anodize, from architectural clear to the bronze and the blacks to the high vibrant colors that you'll see, mechanical finishes, brushing and polishing, as well as screen printing or vinyl printing onto the extrusion itself. Again, talking about the range of finishing, anodizing doesn't have to be just clear, bronze, or black. There are many decorative finishes that can be used, as well as industrial type coatings that will increase, that you'll see on things like hydraulic cylinders and other parts like that. But a very wide range of finishes that can be used in aluminum extrusions or with aluminum extrusions. Again, another example of finishes This one is a particular company based in Minnesota where they're using the high-end architectural finishes for finishing out commercial and commercial spaces. The coral finish is a particular finish of interest where that is applied. It's a combination of, let's say, basically a printing as well as powder coating or paint that comes together to create simulated different types of wood grains to stone finishes to many different things where you can actually, that can be applied to the profiles themselves, and really it really mimics the natural finishes of those different materials, but in a sustainable manner. Talked a little bit about this one before, which was a new project that was just installed this past spring, which is basically a fence around a baseball field down in Texas. In this particular one, we start talking about ease of fabrication. So this is all one extruded aluminum profile that has been assembled together, but then the pattern in the fence is basically machined into the part. So some very unique things that can be done in architectural applications just in the fabrication of the part itself. As I mentioned before, there's a cost-effective aspect to aluminum extrusions, and here on this side we'll talk a little bit about the production cost of the tooling itself, as well as the time that it takes to create that tooling. So basically, with aluminum extrusion, it is has the lowest tooling cost of any of the metal forming processes. So here you can see how it typically, applies to stampings or moldings, die casting, roll forming parts, where you really have a huge upfront investment into the tools themselves. Now, for aluminum extrusion, it's really garnered by the size of the press. So a smaller press, die costs may be between $500 to $1,000. When you start to get into very large profiles that are running on, let's say, 16-inch presses and above, there your die costs are going to be far in excess of $5,000. So there you're probably looking at more like 10 to 15. But still, as you start to compare it with larger parts and some of these other metal forming processes, you're going to see a lot of difference there too. But typically the aluminum extrusion die cost is one of the lowest in metal forming operations. But it's also time effective. So one of the things is typical lead time are between 3 to 6 weeks, depending on the complexity of the die and whether it's a solid or a hollow die. A solid shaped die, will typically be more like 2 weeks to 3 weeks. Whereas a hollow die, which actually requires multiple pieces to create that tool stack, can be on the 4 to 6 week range, but still relatively short when compared to other forms of tooling. A lot of discussion over the years of the sustainability of aluminum. One of the key attributes of aluminum is that it can be recycled over and over and over again without degradation. Recycling is a key part of the aluminum extrusion industry because it only requires 8% of the energy to recycle that aluminum back into a new product than what it does to create virgin aluminum. Obviously, the most energy-intensive part that you'll ever do is create, aluminum from scratch. Again, with the sustainability, we do have through the AEC, we have just completed environmental product declaration, which is available on aec.org. So that'll take you through many of the different recyclability and sustainability opportunities with aluminum. For the second part of the agenda, we're going to focus more on the actual design of the parts themselves. So we'll look at the alloy selection, the extrusion geometry, and then finally the fabrication and the finishing. So some things to consider when we start talking about alloys. Most of the time, what we're talking about in soft alloy aluminum extrusion is 6000 series, which you can see is by far one of the largest parts of the different, offers many different varieties of aluminum alloys within that series. Here in the 5000 series, you'll see mostly that would be your sheet and your plate alloys. So 6000 is really when we're talking about soft alloy extrusions where we focus on. Again, 6000 series is typically or is used as magnesium and silicon are the main alloying elements in that. Within the 6000 series, we have a good strength, we have good corrosion resistance, machinability, weldability, formability. It's also heat treatable, which is key within our process to be able to come up with all the different tempers that are required. And the key design variables, we have the alloys themselves, and you can see this graph here and how the different alloys within the 6000 series, or some of the main alloys anyway, stack on top of each other. 6060 being on the lower end of the strength, going up to the 6082, which is on the high end. So you can see how there is a lot of overlap within these alloys. You know, the commonality between them all is the magnesium and the silicon, which are the main alloying ingredients of that and create the strength. Here you see a comparison on the extrudability index. So as we go higher in strength, obviously the extrudability goes down. So here it's basically from right to left. We're going in increasing levels of harder to extrude alloys. So that's a direct function of the strength of the alloy itself. So again, we'll start to see why here you have the 6000 series, which are right in the middle, which are good extrusion alloys as compared to steel, which are the dotted lines that are going across. The other one that's not the other point on the slide is not extremely easy to pick out, but as you go from right to left, as they get stronger and harder to extrude, you'll also see your cost for extrusion start to rise because they're just slower alloys to produce when we start talking about 7000 series alloys, and then you could also group in there 2000 series and 5000 series alloys as well. So it's important as you start and you begin to understand what the requirements are for your alloys to select the appropriate alloy. And at any time, your extruder partner is definitely there to help you make that selection, depending on the size of press that it's going to go on, depending on what the end-use application is, what are the secondary finishes or secondary fabrication operations that are going to be done to the part. Those will all begin to drive your alloy selection as you're making the parts. Start to talk a lot about geometry, right, and the types of shapes. So this is very important to an extruder. Obviously, not only whether it's a solid shape as what's in the upper left-hand corner, but the hollow shapes as well. And then we also have another kind of category that's called semi-hollow, which obviously it's not a solid, it's not a hollow, because these produce more like a hollow shape, yet it does not have an enclosed void in it within the hollow. So there's different classes. There's within each section. Solids are basically just that. It's a solid shape. Semi-hollows, there's a class 1 and class 2, and then there's 3 different classes on hollows, all dependent on the size, how many voids, and different things like that that we look at when we're evaluating a shape for production. Again, back with the idea profile and talking about the design functionalities. mean, that's key within the geometry. It allows us to join other extrusions together. We can facilitate assembly. You provide additional functionality and enhance aesthetics and everything, all with designing into the extrusions themselves. Good design practices, we typically want to stay away. We like to have, consistent wall thicknesses throughout, smooth transitions, uniform profiles. That's not always an option. This is just a good to. We would like to see, but we can work around most requests all the time. Die tongue ratios is very important to us as we start to talk about the extrusion die itself and the wearability of the extrusion die, because the extrusion die is basically a negative. So everywhere where you see aluminum corresponding on the extrusion die, you'd see a piece of or you won't see a piece of steel. So it's very important to us to talk about die and tongue ratios when we start to look at design and the type of tooling that we're going to need to make the part. Some different key design variables to look at as we go through. So you have the screw slots, as we looked at before. There's different features that you can build in to the screw bosses themselves to give more bite to this. Typically with the screw slot, we'd much rather see this semi-hollow condition versus a full void like that, because this on the bottom right-hand corner is just much more complex to be able to produce. Again, talking about balancing, also talking about ways of getting rid of internal voids, making sure we have generous radius corners, getting rid of the hollow voids in the middle, and just if there are only pockets there to accept a piece of hardware, we can definitely break that surface and have a solid profile right there versus the hollow. Here's another instance of where actually a hollow profile is better to produce than a solid. So you can see in this particular one, we went from a solid profile with very high tongue ratios and added 7 voids, but shortened the tongue ratio, added screw bosses, added assembly features to the profile to basically make a better solution. Plus, with the actual added voids in there, we increase the surface area of the part, so it's actually a better heat sink than what it was before. So we're talking about solutions and designing and geometry. Here's kind of your an enclosure, right? So we have 1, 2, 3 different pieces. So you have a top, you have the bottom, and then you have this little L bracket off to the right that's holding it in place. So instead of making 3 different pieces, we can work on combining pieces and creating features into the part. So instead of 3, now we have 2. And we impart some of the mounting with machining, and add the heat sink, or increase the surface area to this electrical box to increase its thermal conductive properties. It added on the top lid, added the lines, to help with the aesthetics of the part. And then as well added the hinge feature and the screw bosses on the side, so we can cap off the enclosure and get everything assembled and put together. Tolerances is usually a very important part that we like to cover through the initial design process. It's always good to understand what is needed for functionality, the critical features and tolerances. We'd like to have those designated up front. Apply the appropriate tolerances, for non-critical or non-functional features. It's one of those things where, we can't tolerance everything on a part. It's just not, it's not feasible to check. Plus, is it really required? So understanding what you need as you go through. And then another important part is to understand, the inspection methods that we typically use as extruders. A lot of the initial inspection checks are done in line at the press as the extrusion is emerging from the press. We do have a lot of parts that we run SPI data collection on, but that basically happens after the fact, and using the different vision systems and things like that we work. So a lot of it is understanding what do we have to check at the press so we have a good chance of being successful with the part once we get to the end of the production process. The aluminum association standards and data, you'll see this referenced a lot when you receive a print back from an extruder. We'll reference standard aluminum association tolerances. That's this table right here. It's available from the Aluminum Association, or even your extruder partner should be able to get you a copy of that. But it basically covers everything that you would need to know about typical tolerances for aluminum extrusions. We'll start mostly with standard tolerances. We have cross-sectional tolerances. There's twist, straightness, flatness. A newer part within the last few years within the standards and data book is actually the precision tolerance guide. So there is a standard tolerance column, and then there's also a precision tolerance, which is typically 2/3 of standard. At the end of the day, we can usually work around those standard tolerances. Depending on the alloys and the features, the press size and different features like that of the profile and what's going to be required to produce it, we can usually do better than standard tolerances, but most likely the best that we're going to do in a high volume scenario is get down to a half standard situation with the tolerances on there. You can do better, depending on the press and the size of the shape itself. So again, we start talking about variation. We try to reduce variation as much as possible through the process, but it's really dependent on the shape. So we have to be very careful when we're talking about the geometry. But all these different attributes do garner what we'll be able to hold when it comes to the tolerances of the shape and the variation that you're going to see along the cross section. Fabrication and assembly. So obviously, most everything that happens out there, there's something else that's done to it along the way. Whether your extruder is doing the machining, punching, bending, or something else to the assembly operation. So at the end of the day, extrusions and specifically aluminum are very easy to fabricate and assemble. Here's a particular part that's actually the top of a tent pole that's used in a military application, where you can see you start with one profile on the left, and through your welding and machining and assembly operations, we end up with the finished product on the right. Using the attributes of aluminum, here you actually have a speaker cabinet where the whole speaker cabinet is machined and basically tuned to the specific part. Machining, we do a lot of machining, for engine mounts and different parts like that. Replacing castings, which are actually, an extrusion, to replace a casting, depending on the casting process, it's much more efficient and quicker than it is to have a cast part. The range of finishes that we're talking about, we really need to talk about the design. There's things that happen during the flow of the extrusion process, so we like to look at it, especially if it's a hollow profile, the internal features of the profile, so we can minimize the transition areas between the internal walls and the show surfaces, because we don't want any flow lines or anything to be exposed on that. Alloy selection is a big part of the finish and the final finish that you'll receive. So more of the decorative finishes, you're going to see those are going to be the 60-60 or the 60-63 that are on the lower end of the strength scale. But because of that, they extrude with them, and they're much cleaner alloys, so they'll extrude with a much better surface finish on there. So then, final point is just, let's understand what the show surfaces are, what the exposed surfaces are for the part. That's going to help the extruder determine what the runout surfaces is and how we're going to handle and package that for delivery to the customer. So overall, right, so we're talking about kind of a holistic approach to extrusion design. And so number one, the most important point is to get the extruder involved early. That'll help you save time through your iteration process and development because we can put our input in immediately at the beginning and help steer it in the right direction. So we end up with a part that's economical for us to produce and obviously for the company to purchase. But in all that too, we can enhance the amount of the utility of the part and develop the designs that are going to be simple and yet eliminate fabrication steps and assembly steps on the OEM's side. So again, getting the extruder involved at an early stage is important. Converting the steel to aluminum is, it's not necessarily that it's cost effective, but here you have to look at the overall total cost of ownership of the part. And many times you can really get there where the aluminum profile part is actually saving money in the long run. We also have to say a lot of times have a realistic cost expectation with what that part is going to cost. The other thing is we can also work to enhance the experience that we can make small changes to the part that will yield significant savings, and then understand what those tolerance and trade-offs are. So for the most part, the Aluminum Extruders Council, AEC.org, there's a lot of helpful information out there that's very insightful. Most of it is free for the designers to download. This webinar itself will be made available after today. And then along with the Aluminum Extruders Council, you have the Aluminum Association and the European Aluminum Association. With those three in conjunction, work together on a wide variety of different aluminum products. The Aluminum Design Manual is available from aluminum.org. I believe that's a product of the Aluminum Association. There you'll get much more specific design information for the parts. And then here's a list of all the extruder members that are part of the AEC that helped bring this webinar to you today. So at this point in time, I will be taking your questions. Hopefully we have a few minutes left in going through that. So I'll turn it back over to Lisa for questions.
Jason, that's awesome. What a great presentation. Thank you. And yeah, before we jump into the Q&A, we have a poll question, I believe, that might be popping up on everyone's screen right now. I'm just going to give everyone a moment to go through this, and then we'll get started on the Q&A. And yeah, Jason, you're right. There's a big pile of questions here. I think we have a little bit of time. We might not get through all of them, but yeah, this is great. All right, so just as a reminder to all of you attendees there, feel free to enter any more questions you have in that On24 Q&A window there. Many of you have already submitted questions, so we're going to jump right in. Jason, by the way, I'm going to just read the questions as they were submitted. If at any time you feel as though this is a question that requires maybe offline follow-up, if it's very specific, just let me know.
Okay.
So, first question. Is there a guide for wall thickness versus strength for different aluminum alloys?
Well, let's see. So So a lot of that, as far as the wall thickness and the strength and how it relates, so that really is garnered by the profile design. So I guess typically, well, in the stronger alloys, it's harder to get thinner. It's not impossible, but it is harder. So you usually see as the alloy strength increases, the wall thicknesses are going to become larger. Probably not, there's not a direct guide for that itself.
Okay, got it. Next one is extremely specific, maybe offline follow-up, and we're excited to kind of help you out on that, but I'll give it to you anyway. What is the temperature and time for aging 6063 T6?
That's going to vary, but typically, let's say that the typical artificial aging process is, let's call it 8 hours at about 350 degrees.
Very cool. Next question. On a profile of a hollow triangular tube that is 14.5 inches on a side with a thin wall, how thin can that wall section go? How big of a die diameter is needed?
Hollow triangular tube. Wow. So that's a big. I think we might have to follow up on that, but I would say just in general, right? So you're starting to get pretty big as far as circle size of a part, and depending on the alloy. So I would say probably in the U.S. on our typical presses here, maybe about 0.120 of an inch, 120. There are some European presses that operate at a much higher die face pressure. In fact, Sapa has a press in Lichtenvelde, Belgium, that we're in the process of upgrading now, where we're working on going up to 24 inches wide with basically a 2 millimeter wall thickness, so about 80 thousandths of a wall thickness. But in North America, a typical press with the die face pressures we have here, on a profile like that, I would say about a 120 wall thickness in a 6063 alloy would be common.
All right, and I think that we have a follow-up question from the same attendee, but I will send that onward. So to that attendee, just know that we're going to follow up on your follow-up question. And we also just have a few questions about additional resources. I just want to let everyone know that indeed you will get a copy of this archived webinar, as well as some additional follow-up information. Jason, next question. Does the entire cross-section of an extrusion have the same properties, or is there a quote-unquote skin effect?
No, well, it will depend on the thickness of the material. But typically, the entire cross-section of the extrusion has the same properties as far as metallurgical properties. You know, if you're looking at a hollow profile that might have some internal webs, those internal webs might be a little bit different as far as the strength of the webs, because they're not receiving all the quenching as it's coming out of the press, as well as some bigger, just solid chunks of metal, you know, a big bar or a big rod. Depending on the press that would extrude those, you might have some unrefined grain structure around the end. But typically, it's the cross-section of the profile is going to be the same metallurgically from one side to the next.
Excellent. Next question. Are the weld lines in an extrusion visible in metallographic examination?
Yes, they are.
Got it. Next question. As a designer, I have to be concerned with corrosion. What about unfinished aluminum? What do I have to be concerned with or watch out for here?
Typically an unfinished aluminum, so obviously corrosion, aluminum does not rust, however, everything corrodes. It will depend on the environment where it's going into. So if you're into more of a coastal environment, you're going to want to finish that aluminum in some way, anodizing or painting. If you're going to be assembling other materials onto it, specifically steel, we want to make sure that we have some type of buffer in between the aluminum and steel to reduce the amount of galvanic corrosion. You have to be careful with the types of fasteners that you're using. So there's a wide variety of things to watch out for. But typically if you're going, aluminum to aluminum, there's usually not a whole lot of issues. So it's really when you start introducing other materials into the equation that it gets a little tricky. But every extrusion company has some sense of what it takes and can help you out with that.
Cool. This next one is interesting. Can an extruded shape be patented?
The shape itself cannot be patented, however, the end use can. So as part of a product, the extrusion can be patented.
Cool. Next, where aluminum extrusion is concerned, what tolerances can be accommodated in support of component net shape? For example, in a hollow billet with a 2-inch inner diameter, is it actually consistently 2.000 in that inner diameter?
Mm. No, the inner diameter. I mean, if you look through the aluminum standards and data book, they actually go through in the pipe and tube section. They'll start talking about eccentricity and ovality and different things like that. So it does change throughout the entire length of the extrusion.
Excellent. Another question, can you explain more on the vinyl and screen printing application?
I think on that particular one, I mean, we've printed, both laser etched, as well as that the coral process that was referenced before. That's basically laminating, material right onto the extrusion itself. So there's, several manufacturers out there that make equipment, finishing systems to do that.
Good. Jason, we have so many more questions, but we are out of time. So this concludes the webinar. Attendees who have asked questions, please know, again, you're going to get a copy of this webinar, and we will be providing you with answers and follow-up. So Jason, thank you so much. And I'd like to also thank our sponsor. Thank you, SAPA Extrusion North America. And thank you to the Aluminum Extruders Council for this presentation. The on-demand version of this webinar, again, will be emailed to everyone shortly and will also be live at designworldonline.com. Sincere thank you to all of you for joining us.